we have what all the information that we need. We have the surface area and the volume. Now we have to optimize what? Let's check the question. What are we optimizing? Determine the dimension of the box that minimize the amount of the material. So we are maximizing the area or minimizing. Yeah, we are minimizing the area. So it means that here we can make y the subject of the formula. It means that we have 13,500 divided by x squared, and then we substitute on the second equation. So it means our s is equals to x squared plus 4 multiplied by 4x multiplied by 13,500 over x squared, and then this becomes x squared plus, so x and x cancel out, and then 13 multiplied by that, I think is 54,000 over x. Okay, now we differentiate ds over dx, ds over dx. This becomes 2x, 2x. So yeah, that's the step. 2x minus 54,000 over x squared. So here we can write this as x squared plus 54,000 x to the power minus 2. Then we apply the power rule on this one. We'll end up with this answer here. And then we equate this guy to 0. If we equate it to 0, now we can solve here. We have 2x to the power 3 minus 54,000 all over x squared, and this is equal to 0. We have x equals to 0, but we are not interested in that. So we have 2x to the power 3 equals to 54,000. We divide both sides by 2. So we have x to the power 3 equals to 27,000. So x, then we take the cube root of this guy here, 27,000, and this is equivalent to 30. So it means that the value that we have here is x. Now we have to test this value if it's going to give us using the second derivative test. So we are going to differentiate this guy here again to determine the second derivative, to check if indeed is giving us the minimum. So we have dx, dA, we are determining the second derivative over dx with second derivative there. So if we differentiate, we end up with 2 minus, is that the case? 2 minus what? Is plus 2 plus 2 multiplied by 54,000 all over x to the power 3. Now we substitute 30 to see that indeed we are going to get a minimum. To get a minimum, this value must be positive. So this is equals to 2 plus 2 multiplied by 54,000 divided by 30 to the power 3. And our solution here is what? Is 6. So you just punch this in your calculator. Your answer is 6, and 6 is greater than 0. So 6 being greater than 0, it means that we have a minimum. So we have shown that actually our value will minimize the problem. And now you can determine the value for y by substituting here. So I'm going to determine the value of y. Y is equals to 13,500 divided by x squared. So substituting x, our x is 30, so it's 13,500 divided by 30 squared, and this gives me 15. So the value for y is 15. So now we can conclude that the dimension of the box that minimize, you just answer the question, that minimize the amount of material for needed to make a box is what? Is x equals to 30 and x equals to 15. So you should basically just answer this question here, because they say determine the dimension of the box that minimize the amount of the box. So you can just say the dimension of the box that minimize the amount of the material used are x equals to 30 and y equals to 15. So I have solved this problem. You can clearly see that's how you will solve this one. So this is basically an optimization. So I think I'll do as many examples as possible. So if you go to example 3, we say that show that the volume of the largest cone that can be inscribed inside a sphere of radius r is, so they have given you the answer. They want you to prove that this is indeed the situation. Now when they say inscribed, they actually, I have a diagram here. So this is a sphere, and inside the sphere they have inscribed a cone. So from R here represent the radius from 0 to B. This is the radius of the sphere. And then from C to this point is from BC represent, I think this will be a small r. The radius of the cone is BC. And now what is changing here basically is X. Okay, so X is changing. So you must determine the value that will optimize this problem. So X is changing. R is a radius. So the shape of the cone will be determined by the value of X. If X gets closer and closer to 0, what happens? And basically it will depend on the value of X. So let's solve this problem. So they asked us to, what did they ask us to? Oh, we are showing that this is the case. We are looking for volume. So let's solve it. So we'll start with the volume of the cone. The volume of the cone is equals to 1/3 pi r squared h. Now we let, like I said on the previous, r to be the radius of the cone, and then there is given that capital R is the radius of the sphere. I think I left out P of the sphere. Now from the diagram here, you clearly can see that BC, where is the diagram? BC is equals to R. So BC is equals to a small r. Now we need to express BC or R in terms of R and X. Now I'm going to focus here. Here we have a right angle triangle. Can you see this one? Triangle, we have triangle L, I don't know where to start, O, C, and B. So in this triangle, we have R and X. So we can clearly see that R squared here, this R, is equals to X squared plus small r squared. So we want to make this small r the subject of the formula. We can clearly see that r here is equals to the square root of r squared minus x squared. And basically this means that BC is equals to that, r squared minus x squared. So here I was just looking for the value of BC. So now we are going to use this value here. We said this is equivalent to the square root of r squared minus x squared. Okay, now h, what is the value of h? Looking at the diagram, you can see that h, this is the height of the cone. From this point to this point, this will be the value of h. So this is our h. You can clearly see that h is equals to r plus x. So our h is equals to r plus x. Now we substitute in this formula here. So substituting, we have v equals to 1 over 3 pi. Then we substitute our r squared minus x squared. So let me write it this way, multiplied by r plus x. So you can see that the square root and squared, they cancel out. Our equation becomes 1 over 3 pi r squared minus x squared multiplied by r plus x. Now let's simplify this by getting rid of that those brackets. So multiplying out, we have r cubed plus x r, is it xr squared minus x squared r minus x to the power 3. So now this is our volume. Now because the x is changing, so we differentiate v with respect to x. So you have 1 over 3 pi, and then when you differentiate, this is 0 because we are differentiating with respect to x. So this will be r squared minus 2xr minus 3x squared. Now then we equate this to 0. So here, what do? You factorize this guy, 1 over 3 pi. Now we have r, and here is r, 3x, and x. Now we want the bigger one to be negative. So this will be positive, and this will be negative. So now we can check if we get the middle term. So the inner and the outer must give us the middle term. So the inner is xr, the outer is minus 3xr. So if you subtract these two, we get the middle term. So this means my factorization is correct. So this is equivalent to 0. So we have x equals to minus r, and we are not interested in this. It's negative, we want a positive answer in this case. So we have x equals to 1 over 3r. Okay. Now what we need to do, are we optimizing or minimizing here? In the question, they said we must determine the largest. Okay. So what do? You can test if this value is going to give you the biggest number. Let's just do that. We determine the second derivative. The second derivative, I think I wrote it, this is not correct. So this will be v. No, I was correct. Okay, this is equals to, now I'm going to differentiate this one here with respect to x. So I'll keep the constant. So this is 0. Differentiating this one is going to be minus 2r minus 6x. Now substituting my value of r here, let's see what we get. It's 1 over 3 pi minus 2r minus 6 multiplied by 1 over 3. This is r, yeah. So in this case, 3 and this one cancel out. We have what? Minus 4r. We have minus 4r over 3 pi. So we can see that this is less than 0. So this means we have a maximum. So we have tested that. Now let's check v is equals to what? So now we are going to substitute this value of x. Where? I think we can substitute it here to see that indeed is going to give us the value that they are looking for. So let's see. So we have pi over 3. I want to copy the equation that I'm going to substitute in. It's r squared minus x squared, r plus x. So I'm substituting, I'm looking for the volume at r over 3. So I'm substituting r over 3. So it's pi over 3 r squared minus r over 3 squared multiplied by r plus r over 3. So I want to determine if I'm going to get that value. So it's pi over 3. So this is r squared minus r squared over 9. And here what do I have is 4r over 3. So let me simplify this bracket here. So it's pi over 3. So here I'm using the lowest common denominator, which is 9. So this will be 9r squared minus r squared multiplied by 4r over 3. So this is pi over 3. Adding this is 8r squared over 9 multiplied by 4r over 3. So multiplying out here, let's see, this is 32r cubed. We have 32 pi r cubed, and then 9 multiplied by 9, this is 81. So now let's check if this is what the value that they were looking for, 32 pi r cubed over 81. So we have shown that indeed this is the case. We have proven that. Okay, so you have to follow those steps that I have shown you there to show that this is indeed the case. Okay, so this is optimization problems. Okay, let me check something. EMA 105B notes. This is empty. So basically this problem, I think I took it from, I think it's from here. Optimization, let me use this parametric. I think I jumped it somewhere here. So I basically took it from these notes that we used last year. I've given to one of our lectures to students who are complaining about 1, 2, 3 to change. I'll just ask him after class if he managed to finish. If he's not finished, he didn't finish, I'll just give you these ones. Parametric. Yeah, this is the problem. This is the problem. It's a number. I took it from here. This problem, number 3. So I'll just put these nodes on bright space after confirming if there's any change. Okay, so you can do the remaining ones. You see it's 1.7. We have about 12 problems, 11 problems. Okay, so that's where I've got the problem. Now, where is my notes? Let's go back here. So I've shown you that this is indeed the case. Now, example 4, an automobile manufacturer is testing a new engine. One of its new model found that the efficiency E in percentage of the engine as a function of speed S in kilometers per hour of the car was given by E equals to 0.768 S minus 0.0004 S cube. What is the maximum efficiency of the engine? So here, what will play the most important part? I need just to copy this equation here. So they've actually done a lot of work for us. So we'll actually start by differentiating this and equate to 0. Determine the value of S at the maximum point. So that's what we are going to do. Okay. So let's go to our board here. So we are given E equals to 0.768 S minus 0.004 S cube. So you differentiate with respect to S. We have 0.768 minus 3 multiplied by 0. I think I left out 1 0 here. Multiplied by 0.00004 S squared, and we equate it to 0. We solve for S. So S is equals to the square root of 0.768 over 3. I think I should extend 3 multiplied by 0.004. Okay, and this is equals to plus or minus 80. If you press that in your calculator. Okay, now you differentiate this guy again. You want to test, you have two values. You must get one value that's going to give you a maximum and a minimum. So dE ds, so you determine the second derivative. You want to test which value is going to give you a maximum. When you differentiate now, you have minus 6 multiplied by 0.0004 S. Now substituting this value of S, if you substitute, and this basically is minus 0.003, since 20, this is 2, 4, yeah. So we end up with this. Now, substituting, we have e to the power, substituting minus 80, we'll verify that. This gives us a positive 0.0192, and this is greater than 0, so this will give us a minimum. And then if you substitute 80, you end up with minus 0.0192 less than 0. This will give you a maximum. So we go back to the question. According to the question, they are looking for maximum efficiency. So this means we get maximum efficiency at 80. Okay. Now we are looking for E. E is equals to 0.768 multiplied by 80 minus 0.00004 multiplied by 80 to the power 3. So our answer here is approximately equals to 41%. So we are going to get a maximum efficiency at E equals to 41%. So we can even verify this by plotting a graph. So I've plotted a graph here. So according to this graph, we can see that equation that we have here. We have 0.768x minus 0.004x to the power 3. So here I just prepared to use x. There's nothing wrong with that. X label. So it's E is a function of S. So this is the graph. You can clearly see that around here somewhere, this is 20, 40, 50, 60, 80. So at 80, here at this point, we'll have a maximum efficiency and we'll have a minimum efficiency at 80 minus 80 here, when s is equals to minus 80. So this means I was just testing if indeed this solution makes sense. Now it makes sense in that case. So we have answered the question. Our maximum efficiency will occur at 41%. And then from the graph, you can see here, it will occur, each ES will be equals to approximately 41 there. That's the answer that we got. Okay. And now the last one. An aluminum can needs to be constructed which can hold 150 centimeter cube. The cost of aluminum is 3 cents per square centimeter for the side, and the bottom is 5 cents per square centimeter of the top. Find the dimension of the can that minimizes the overall cost to construct the can. Okay, so this means here we will need the volume of a cylinder, because a can, so if we check here, oh no, I don't have it there. Okay, let's take the values. You should remember that the cost of aluminum is 3 centimeters per square centimeter for the side and the bottom. So you must remember this information here. You can take a picture. Now we can go and solve this problem here. Now let's start with the can. Let's say this is the can. It will be in the form of a cylinder. This is my can. And now to construct, we are going to have, this is the case. This is my rough sketch, just my rough sketch. So we have 2 cycles. The first one here, we have a radius here, which is r, and this one, the area is given by pi r squared, and here we have 2 pi r, and this is our h, our height. So also here we have r. So the volume of a cylinder, the surface area, is equals to 2 pi r squared plus 2 pi r h. Now from here we can make our cost. Our cost will be equals to 3 multiplied the bottom. For the bottom is 3 multiplied by pi r squared plus 2 pi r h multiplied by 3, is our sides, plus 5 multiplied by pi r squared for the top. So now we have the formula, which simplifies to 8 pi r squared plus 6 pi r h. Okay, and we know that the volume of the can is equals to pi r squared h. Now from this one here, we know that they said this is 150. Now this implies that h is equals to 150 divided by pi r squared. Now we are going to substitute it here, which you can just substitute here actually. So c is equals to 8 pi r squared plus 6 pi, then we substitute the value of h, we forgot the r, is 150 over pi r squared. So r and r, they cancel out. This means this becomes 8 pi r squared plus 900 over r. So r what? Pi and pi also cancel out. So pi and pi cancel out, r and r cancel out, then here you remain with just 1 r. Okay, now you differentiate c with respect to r. So you have 16 pi r minus, so this can be equals to 8 pi r squared plus 900 r to the power minus 1. So that's where I got the negative. So it's going to be 900 over r squared. Then we equate this to 0. By equating this to 0, we end up with 16 pi r cubed minus 900 all over r squared. So we are not interested on r squared, r equals to 0. So it means that here r cubed is equals to 900 over 16 pi, isn't it? Then we take the cube root. So this means r is approximate, this implies that r is approximately equal, I think it's 2 point something. What did I get there? 2.62. 2.62 by solving this one here. Now, to test if indeed we are going to get the maximum or minimize the cost, so we have to test by using the second derivative test. So from the second derivative test, we differentiate this one. It's going to be 16 pi minus plus 900 r to the power 3. It's not 900. I think it must be different. It's 1800 because you're going to multiply by 2. So it's 1800. Okay. Now, from this one, you can see we have positive in all of them. So I can conclude this implies that C 2.62 is greater than 0. And this gives me what? A minimum by the second derivative test. Okay. So this gives me a minimum. Now I'm going to determine the value of H. H is equals to, so we can go up and check where we can substitute to determine 150. 150 divided by pi r squared. So we are going to substitute the value of r. So it's 150 divided by pi. What? We substitute 2.6. 2.62 squared. So this is approximately equals to 6.96. Okay, now we go back to the question. What were they looking for? Find the dimension. So now we can conclude that the dimensions that minimize the overall cost of the construction of the cairn are what? Are x, not x, are r equals to 2.62 and h equals to 6.96. So those are the dimensions that will minimize the construction. So you are answering this question. You can say the dimensions of the cairn that minimize the overall cost of the construction of the cairn are r equals to this and h equals to that. Okay, so we have managed to answer that question. Now, if you go back here on the last one, so this one will be your homework. So remember, in that case, it was a sphere inside a cone. Now we can also put what? A cone. No, that one was it's another way around. The one that we have solved there above, it was, we can go and check it. It was a sphere inside a cone. So it was a sphere, a cone inside the sphere. So it was a cone inside the sphere. Now we can also put a cone inside the sphere. And in this side, we want the minimum volume of the cone. Okay, so I think this will be your homework just to practice. You can go and find out more information about this one to practice. It's not straightforward. It's going to be demanding. I think I solved it here. So the correct answer for this one, I can give you the answer. The correct answer will be the minimum volume will be equals to 8 over 3 pi r cubed. So I'm expecting you to get this answer here for this one. Okay. So I think I'm done for the day. I can take your questions. Let me save the record. Okay, any questions? Any questions related to this optimization? So for optimization, we'll always get at least one question in the major test. I think it will be in the major test 3, which maybe you are going to write. Story.
Yes, sir. Good morning.
Morning.
Sir, I just want to know if you might be able to convert the notes that you made on OneNote and like convert them into a PDF and send them to us, if you can.
I don't know. Let's check if we can save. It's got share there. I don't know how do you share. Share with the meeting. We can print it. Let's print this one and see. So the last one we're solving which problem is a cost problem. Let's just say cost problem. So you'll relate to this. Let's just put them inside a folder. Optimization. Okay, rename. Optimization problems. Okay. This one is number 83. Let's go and check the other one. 82. And then we say this one, what are we solving here? Or efficiency problem.
Sorry, sir, you were breaking a little bit there. We didn't get that.
No, I'm saving this one because I'll forget. I just want to send them before the end of the class.
Oh, all right. Thank you.
Yeah, otherwise I might forget that. If I send them now, I think you'll be on the safe side also. So I'm just trying to do it now while you are still there. You can just wait for a while.
Right, so no problem.
Okay. And then this problem, what is the name of this one? Sphere and cone problem. I'll just write it like that. Then I'll attach everything there. This was page 81. Let's go to 80. Box. What's going on? I didn't see it printing.